Hey folks, the next thing we're going to look at is finding volume of a solid of revolution. And in this section, we're going to focus on the disk method, which also will give rise to the washer method. That's why I call it the disk/washer method. So if we take a region in the plane and we revolve it about a line, we get a solid that is called a solid of revolution. So in the prior section, we looked at finding the area of a region in the plane. Well, now we're going to revolve that region around a line to get a solid of revolution. And the line that we revolve the region about, we're going to call that the axis of revolution. Now, the easiest or the simplest of these solids of revolution is called a disk. And at this time, I'm going to head off to the chalkboard and we're going to analyze what a disk would look like. You can kind of think it looks like a quarter or a nickel. The importance of sketching a representative rectangle, which we discussed in the prior section, it's going to become apparent when analyzing, the disk method and the washer method, as well as the next section when we look at the shell method. So let's head off to the chalkboard and let's analyze the simplest of these, which is called a disk. All right, folks, we begin our study of solids, of volumes, finding the volume of a solid of revolution by looking at the disk method. So just to recap what we've seen so far, here's a line that's called the axis of revolution. I use this kind of a symbol to indicate it's the axis of revolution. And this is a rectangle. I'm going to end up calling it a representative rectangle. And I've labeled the base as W. It's kind of like the width. And I've just labeled the height as an R, an uppercase R. And you'll see why in a moment. When this one rectangle, just this one rectangle, gets revolved around this axis of revolution, it produces what is called a disk. Now, here's what a disk looks like. It's the closest thing I have to what a disk would look like. No surprise, Ohio State paraphernalia. But when it gets revolved around, this is what it would look like if you're looking at it edge on. So it gets revolved around, that's what it looks like edge on. Now if you change your perspective and look at it from the side, you look at that disk, this is what it would look like from the side. This is a disk. This is one disk. How do we find the volume of this one disk? So let me write that up here. The volume of this one disk. So let's think about this. What does that look like? I mean, it's a circle. So if we could find the area of the circular face of the disk and multiply it by the thickness of the disk, wouldn't that give us the volume of this one disk? Yes, it would. And so let's continue. Let me put that down. So let me just write down what we just kind of said, what I just kind of said. The area of the circular face times the width. Well, that's nothing more. I'll keep writing this down. Finding the volume of one disk. Area of the circular face, well, that's just the area of a circle times the thickness or the width of the disk. So the volume of that one disk. Okay, now how do we get the area of the circular face? Well, let me grab it one more time. So the rectangle gets revolved around, so it looks like edge on. This is the circular face, the area of the circle. The area of this circle, isn't that just pi r squared? Yeah. So it's pi r squared, big R squared, times, well, the thickness of the disk or the width of the disk is just W. So that's the volume of a single disk, just one disk. So let's head back to the slides real quick to see what this is going to lead to. All right, we have just seen how to determine the volume of a single disk. That came about from looking at one rectangle. We know that in a region that we can sketch in the plane, we could put many rectangles that which, when revolved around an axis of revolution, would produce many disks. But we use a single rectangle. Keep in mind, I call that a representative rectangle, which would then be used to represent all of the disks. Remember, integration is the process of slicing into many small pieces and then adding. It's the limit of a sum. So let's head back to the chalkboard to write down the definite integrals used to find the volume of a solid of revolution using the disk method. All right, it's time to come up with the formulas for the disk method. Remember, the last thing that we had seen here at the chalkboard was that the volume for a single disk, just one disk, was pi r squared times W. R was like the height of the rectangle, big R was the height of the representative rectangle, and W was the thickness of the rectangle. So we know the game of integration. The game of integration is you slice it into a bunch of smaller pieces and then add them all up. You know, it's a limit of a sum. So with that in mind, we could put in, for a horizontal axis of revolution, so here's the horizontal axis of revolution, this region that I have shaded, we could put in a whole bunch of rectangles. There would be a whole bunch of disks when we revolve the region around this horizontal axis of revolution. We just use one rectangle, the representative rectangle, and then we do the limit of a sum concept. Add them all up, do the limit of a sum, a definite integral. So let me sketch in that one representative rectangle. Remember in the prior section I stressed representative rectangle would be very important. When we got to this section, when we did the volume of solids of revolution, let me label this one representative rectangle. The base is delta x, the width is delta x. And while this is going to be some function of x, I'm going to label it with big R of x to remind me that it's determining the height of this rectangle. It's determining the radius of the circular face of the disk. So then, the volume. Well, it's pi r squared. One disk, it's pi r squared times W. Here, it's the integral from A to B. Limit of a sum, we're adding them all up. Integral from A to B. Let me put the pi out front since it's a constant. R squared, so that's whatever that function of x is, R of x squared dx. Now some people keep the pi in here, but since it's a constant, I rip the pi out in front of the integral sign. So that's what we have when it's a horizontal axis of revolution. Similarly, for a vertical axis of revolution. So here's my axis of revolution, the little symbol indicating that's what we're revolving around. I'd put in one representative rectangle. I kind of shade it here. Thickness is delta y. The height, which will be the radius of the circular face, that's R of y. So the volume, add them all up, do the limit of a sum. It's pi r squared. So pi, Limits of integration are c to d, r, so I have that as r of y, squared dy. Remember one more thing, delta x dx, this is a function of x. Delta y, integrating with respect to y, this is a function of y. And let me put one more note up here. Let me give this I'll make this a 4-star comment. Our variable of integration whether or not it's dx or dy, is determined by the representative rectangle. And note that the representative rectangle, in both situations, note the representative rectangle is perpendicular to the axis of revolution. You're going to hear me say this a lot coming up in the rest of this video. Not only is the representative rectangle, in the disk method, not only is it perpendicular to the axis of revolution, but notice that it's touching or resting on the axis of revolution, here as well as here. That's a distinguishing feature to tell us we're going to use the disk method. So there it is. There's your disk method. Now let's head back to the slides and see what is next. All right, now that we see the formulas we use for the disk method and we see where they come from, basically, the pi r squared, that's a big clue in there. Let's look at an example. Let's find the volume of the solid that's formed by revolving the region bounded by the graphs of f of x equals square root x, the x-axis, and the line x equals 3. So we're going to take that region, we're going to revolve it about the x-axis, and we're going to find the volume of that region. So just kind of looking ahead before I head off to the chalkboard, you must begin these problems by first sketching the region, seeing what it's being revolved about, and using a representative rectangle as a guide. So hopefully you have this example written down because I'm going to head off to the chalkboard and work through it. All right, in this first example, we're asked to find the volume of the solid formed by revolving the region bounded by the graphs of f of x equals square root x, the x-axis, and the line x equals 3. That region gets revolved about the x-axis. Okay, first thing you may notice is that up here on the board I just wrote blah in quotes. Blah is going to be my shorthand for find the volume of the solid formed by revolving the region bounded by the graphs of. Because all these examples, they all start off with the same words. So I'm not going to keep writing all those words down. So I've already gone ahead and done the first thing you need to do. We need to sketch the region. This is a lot like what we did in the prior section. Here's the graph of f of x equals square root x. Of course, we have the x-axis. X equals 3 is the vertical line, x equals 3. The region that's bounded, well, it's this region here. And that's the region that we're going to revolve about the x-axis. So this region gets revolved about the x-axis. I put in a representative rectangle. This whole process sounds the same as what we just did in the prior section. So here's my one representative rectangle. The base of this representative rectangle is delta x, And now the height of that representative rectangle. Well, the height of the representative rectangle is given by f of x. It's square root x. But I'm not going to call it f of x equals square root x, because in using the disk method, I like to call it big R of x. Because it's telling me that's what is producing the radius of the circular face of the disk. So then to find the volume, it's pi r squared. Pi, the radius of that circular face, square root x squared dx. The limits of integration, well, 0 to 3. Those are the limits of integration. 0 to 3. Now we just do it. I mean, when you take the square root of x and square it, you get x. The antiderivative for x is just a 1/2 x squared. Evaluate that from 0 to 3. Well, 3 comes in for x. 3 squared is 9. 1/2 of 9 is 9 halves. 9 halves times pi is 9 pi over 2. Minus, well, when 0 goes in for x, you get 0. So this is it. This is what the volume of that solid of revolution would be. Okay, now technically speaking, there would be units attached here. So it's some sort of, technically speaking, cubic units, because we found a volume. So there would be cubic units involved. But I'm okay if you don't write cubic units each time. If you tell me the volume is 9 pi over 2, I know that you know that those would be some sort of cubic units, whatever the units involved happen to be. It's not too bad, folks. So again, it's just like the prior section. Sketch the region. Put in a representative rectangle. That gives you the guide for finding the volume. So just to practice this, to make sure you're getting dialed in with the disk method, I would like you to try number 19. So pause the video, do number 19. Once you've finished number 19, restart the video, and I'll be here at the board working through to make sure you have the correct answer. All right, folks, in number 19, you were asked to find the volume of the solid form by revolving the region bounded by the graphs of y equals 4 minus x squared, y equals 0, x equals 0. So that's the x-axis, y-axis, respectively. Taking that region and revolving it about the x-axis. All right, the book was kind of nice here. The book already did the most important part on these problems, sketch the region. So the book already gave you a graph, and I've already reproduced the graph over there. I should put in a representative rectangle. First off, this region is getting revolved. It's getting revolved around the x-axis. So let me put in a representative rectangle. Base is delta x. The height, which gives me r of x, is 4 minus x squared. I notice that my representative rectangle is perpendicular to the axis of revolution, and it's touching or resting on the axis of revolution. That's going to tell me in the long run to use the disk method. So here we go with the disk method. The volume equals pi. Limits of integration, 0 to 2. R, big R, is 4 minus x squared, quantity squared, dx. Pi r squared dx. So we got a little bit of work to do here. Let's prep the integrand. So we take 4 minus x squared and square that. So 4 minus x squared times 4 minus x squared. That gives us a 16 minus 8x squared plus x to the 4th. dx. Get an antiderivative. So an antiderivative would be 16x minus 8/3 x cubed plus a 1/5 x to the 5th. And then we evaluate that from 0 to 2. So let's see, the 2 goes in first. So that's a 32 minus, see, 2 cubed is 8. 8/3 times 8, that's 64/3. 2 to the 5th is 32. 1/5 times 32 is 32 over 5. Minus pi, and when the 0 goes in, you get 0. So, yeah, I'd use my calculator to take care of all these fractions here. And we end up, and hopefully you got this, the volume is 256 pi over 15. Yeah, I know, cubic units. 256 pi over 15. And that's all there was for, this wasn't an example, I'm sorry. This was number 19. So hopefully you got that for number 19. Let's head back to the slides and see what is next. All right, that example wasn't too bad, and hopefully you were able to, get number 19 that I asked you to do. Some things to keep in mind. You have to sketch the region. You have to use a rectangle, representative rectangle. And just to kind of summarize this stuff before we continue to another example, let's look at the process that I highlighted in the first example. Specifically, I said the first thing we should do is sketch the region. Then put in a representative rectangle. That is important. Then the third thing, if the representative rectangle is perpendicular to and touching the axis of revolution, we use the disk method to write the definite integral and find the volume of the solid. This is important. It's a distinguishing feature for using the disk method. It is going to be your clue that you need to use the disk method. You put in that representative rectangle. If it's perpendicular to the axis of revolution and it's touching the axis of revolution, that's your signal. Use the disk method. So let's do another example. Let's find the volume of the solid formed by revolving the region that's bounded by the graph of f of x equals square root cosine x. The x-axis, just on the interval negative pi over 2 to pi over 2. And we're going to take that region and revolve it about the x-axis. So hopefully you have this written down because I'm going to head off to the chalkboard to work through this example. All right, here's another example. Find the volume of the solid formed by revolving the region bounded by the graphs of f of x equals square root x. The x-axis, just on the interval negative pi over 2, less than or equal to x, less than or equal to pi over 2. And we're going to take that region and revolve it about the x-axis. So it's this region here that we're going to revolve about the x-axis. So I put in a representative rectangle. Doesn't matter if I put it over here or over here. I'm just going to generically put my representative rectangle right there. And I kind of shade it. The base is delta x. The height of that representative rectangle, which gives us the radius of the circular face of the actual disk, big R of x, is the square root of cosine x. So the volume, using the disk method, because note, one more time, let's notice this. That representative rectangle is perpendicular to the axis of revolution, the x-axis, and it's touching or resting on the axis of revolution. That tells me disk method. So the volume is pi. Limits of integration, negative pi over 2 to pi over 2. Big R, square root of cosine x squared dx. So we got to do a little cleaning up here. Square root cosine x squared. Well, that's not too bad. That just gives us cosine x. Antiderivative of cosine x. Well, the antiderivative of cosine x is just sine x. And we evaluate that from negative pi over 2 to pi over 2. Let's see, that gives us pi. Okay, the sine of pi over 2 is 1 minus pi, the sine of negative pi over 2, so I'm thinking the unit circle, sine of negative pi over 2 is negative 1. So we have pi minus negative pi, pi plus pi, 2 pi. So that volume would be 2 pi. Yeah, I know, cubic units. So I'd like you to practice another one of these. In the book, go to the exercises, do number 27, and you know the drill. Pause the video, do number 27. Once you complete number 27, restart the video, and I'll be here at the board working through it. All right, number 27, you're asked to find the volume of the solid formed by revolving the region bounded by the graphs of y equals cosine x on the interval 0 to pi over 2, y equals 0, x equals 0, x-axis and y-axis, you know, they're respectively about. We're going to revolve it about the x-axis. So here's the graph of cosine x, just on the interval 0 to pi over 2. Here's the y-axis, here's the x-axis. So it's this region that's bounded by those graphs. It's that region that's going to get revolved around the x-axis. I put in a representative rectangle. The base is delta x. The radius, well, it's cosine x. And yes, that representative rectangle is perpendicular to the axis of revolution, and it's touching or resting on the axis of revolution. That means disk method. So the volume is pi times the integral 0 to pi over 2. R, just cosine x, squared dx. So it's pi times the integral to 0 to pi over 2 cosine squared x dx. Hey, it's something that we need to remember from back in Calculus 1. It's the power reducing identities, you know, to help us integrate cosine squared x. So remember, let me write that over here. The power reducing identity for cosine squared x, it's 1/2 times the quantity, 1 plus cosine 2x. So I replace the cosine squared x with 1/2 quantity 1 plus cosine 2x. And then I would rip the 1/2 out front. So I get pi over 2 integral 0 to pi over 2 1 plus cosine 2x. And let me just pull that right up here. Get an antiderivative. So let's see, antiderivative of 1 is x. Antiderivative of cosine 2x. Well, we know the antiderivative of cosine is sine. So it's going to be a sine 2x. And then we have to remember to put that 1/2, to put a 1/2 in front. So remember, if you were to differentiate this, you'd have to use the chain rule. The derivative of 2x is 2. So you have to neutralize that. Evaluate this from 0 to pi over 2. So let's go through it. I'll put this step in. You'd have pi over 2 times, okay, pi over 2 comes in for x. Okay, so pi over 2 comes in for x. 2 times pi over 2. Well, that's pi. Sine of pi is 0. That's not too bad. Minus pi over 2 times, okay, 0 comes in for x, so you get 0 plus 1/2. 2 times 0 is 0. The sine of 0 is 0. So all of this here ends up being 0. This is 0. So you just have pi over 2 times pi over 2. That's a pi squared over 4. So the volume is pi squared over 4. Yeah, I know, cubic units. Pi squared over 4. Hopefully you got pi squared over 4 here for number 27. That's all there is to 27. So let's head back to the slides and see what is next. All right, after doing that example, I asked you to do number 27. Again, you got to sketch the region. And in number 27, you were reminded of the fact that, the power reducing identity, it's still something you need to know. That may be important in doing some of these integrals. It's with you for the rest of your calculus career. So continuing on, let's look at another example. Let's find the volume of the solid that's bounded by y equals x squared, y equals 4, and we're going to take that region and revolve it about the line y equals 4. So, I'm going to head off to the chalkboard to work through this example. All right, this example, find the volume of the region bounded by y equals x squared, y equals 4. And we're going to take that region and revolve it about the line y equals 4. So here's the graph of x squared. Here's y equals 4. So the region that's bounded by y equals 4 and y equals x squared is that region. And we're going to revolve that region about the line y equals 4. So I put in my rectangle, and it doesn't matter where I put this rectangle in here. So let me just arbitrarily put the rectangle here. The base of the rectangle is delta x. The height of the rectangle, which gives us r of x. Well, this should be familiar. This is kind of like something we talked about in the last section. The height of the rectangle is the top curve minus the bottom curve. So the height of this rectangle is the top curve, which is 4, minus the bottom curve, which is x squared. Another way to think of it, another way to look at it is from y equals 4 to the x-axis. That's 4 units. Let me write that in here. From y equals 4 to the x-axis. That's 4 units. From the curve itself to the x-axis. So from the curve itself to the x-axis, that's given by x squared. It's x squared units. So this height has to be, whatever it is, when you take this height and add it to this height, x squared, you better get 4. That's just another way to look at it. But I like to go back to what we did in the prior section. Top curve minus the bottom curve. And notice that representative rectangle. It is perpendicular to the axis of revolution, y equals 4, and it is touching or resting on the axis of revolution. That tells me disk method. So the volume equals pi Limits of integration. Oh, we have to find our limits of integration. Well, so that means we need to find those points of intersection. This is pretty easy to find those points of intersection. You set the two functions equal to each other, and you immediately get plus or minus 2. So the x-coordinate of that point is negative 2, and the x-coordinate of that point is 2. Radius, 4 minus x squared, squared. So, yeah, let me keep moving on here. Take a 4 minus x squared and you square that. You get 16 minus an 8x squared plus an x to the 4th dx. And let me just stop right here and say I could take advantage of the fact that we have an even function here. That region is symmetric about the y-axis. The interval of integration is symmetric about the y-axis. So I could use symmetry here. I could change this to integrating from 0 to 2 and then multiply by 2, put a 2 out front. I could do that. I'm not going to. I only mention it because if you wanted to, you're going to get the same result. So yeah, antiderivative, 16x minus 8/3 x cubed plus 1/5 x to the 5th. Evaluate that from negative 2 to 2. And yeah, I put the 2 in for the x's, minus then putting the negative 2 in for the x's. And I end up with, and I use my calculator for that, 512 pi over 15. So that's the volume. Yeah, I know, cubic units. So that's the volume. So just to practice one of these, because we revolved it around something different than the x-axis, pause the video, do number 45. After you've done number 45, restart the video. I'll be here at the board working through it to make sure you have a correct answer. All right, number 45, the region that was described that you're supposed to find the volume of the solid of revolution. The region was described as being bounded by y equals 1 minus square root x, y equals 1 and x equals 1, and we're going to revolve that about the line y equals 1. So I've gone ahead and I've sketched in 1 minus square root x, y equals 1 and x equals 1. And now I need to determine what the region is. And we have to be careful here. It's not this region right here. This region here would be bounded by 1 minus square root x, x equals 0 and y equals 0. The region in question is this region that we're revolving around the line y equals 1. So let me put in a representative rectangle. So it would look like this. Yeah, I kind of shade it. So that's square root x. Now the height of that representative rectangle, r of x, is the top curve, 1, minus the bottom curve. The bottom curve is the quantity 1 minus square root x, which, notice this simplifies to just square root x. So the volume equals, notice that rectangle. It's perpendicular to the axis of revolution, and it's touching or resting on the axis of revolution. That means disk method. Disk method, pi, integral. Limits of integration are going from 0 to 1. R of x squared. So that's square root of x squared. So this isn't too bad. Square root of x squared is just x. Antiderivative of x is 1/2 x squared. Evaluate that from 0 to 1, and you end up with the volume being pi over 2. I know, cubic units. Volume's pi over 2. So hopefully remember 45. That's what you got. So let's head back to the slides and see what the next thing we're going to look at is. All right, that example wasn't too bad, and hopefully you did okay with number 45. Continuing on, another example. Let's find the volume of the solid formed by revolving the region that's bounded by y equals 4 minus 2x, the x-axis, and the y-axis. We're going to take that region and revolve it about the y-axis. So let's head off to the chalkboard to work through this example. Okay, in this example, we're asked to find the volume of the solid of revolution when the region that's bounded by the graphs of y equals 4 minus 2x, the x-axis and the y-axis, when that region is revolved about the y-axis. So over here I've already graphed y equals 4 minus 2x in the x-axis and y-axis. So it's this region right here that's going to get revolved about the y-axis. So the type of rectangle I have to put in here in order to use the disk method, the rectangle that would be perpendicular to and touching the axis of revolution would be a horizontal representative rectangle. So here's the horizontal representative rectangle. Let me kind of shade it in. Remember, the base is delta y. The height is a function of y. So we have to take the curve, or the line, y equals 4 minus 2x, and we have to rewrite that as a function of y. So we saw this in the prior section. It's pretty easy for this one. We just have to take y equals 4 minus 2x and solve it for x, because we can think of x as being that function of y. So it doesn't take too much to solve this for x. If I add 2x to both sides and subtract y from both sides, then divide both sides by 2, I get x equals 2 minus 1/2 y. So r of y, this line as a function of y, is 2 minus 1/2 y. And I have to do that because it's a horizontal representative rectangle. The base is delta y. When the base is delta y, that means my integral is going to have a dy. I have to integrate with respect to y. If I'm integrating with respect to y right now, I need my integrand to be a function of y. So here we go, volume, disk method, pi, integrate. Okay, now my limits of integration, because it's a horizontal rectangle, it could go from here, which is a lower limit of 0, up to here, an upper limit of 4. So I'm integrating from 0 to 4, 2 minus 1/2 y, quantity squared dy. So let's just take the 2 minus 1/2 y and square it. So 2 minus 1/2 y times 2 minus 1/2 y. That gives me a 4 minus a 2y plus a 1/4 y squared. And, well, we get an antiderivative. See, that's a 4y minus a y squared. Antiderivative here. See, the new exponent would be 3. The little multiplier in front would be a 1/3. So 1/4 times 1/3 is 1/12. Okay, evaluate that from 0 to 4. So we have pi, put a 4 in, so we had a 16 minus, Ooh, that's nice. 16 minus 16 plus, let's see, 4 cubed is 64. So 64 times 1/12, that's 64 twelfths. Minus pi times, and now 0 comes in for the y's, and we get 0. So like I said, that cancels out. And 64 over 12, that reduces down to 16 over 3. So the volume is 16 pi over 3. So there was an example where we had to use a horizontal representative rectangle. So let's head back to the slides to continue with this section. And I believe when we head back to the slides, we're going to start discussing what's called the washer method. All right, folks. So far we've done several examples, and I've asked you to do some of your homework problems using the disk method. Hopefully you're feeling pretty comfortable with it. Continuing on in this section, if the representative rectangle, if it's perpendicular to, but it's not resting on, or it's not touching the axis of revolution, a hole in the solid of revolution will be produced. So it's perpendicular to the axis of revolution, but it's not touching the axis of revolution. When you do the revolution, you're going to get a hole in the solid, kind of like a donut. And to get a better idea, a better picture of it, let's head off to the interactive ebook to get a quick visual of this. Let me pull up the interactive ebook. All right, so we're going to take this region that's highlighted in green here, and we're going to revolve it around the x-axis. So notice there's a rectangle. There's one rectangle sketched in there, the representative rectangle. Notice the rectangle is perpendicular to the axis of revolution, but it's not touching the axis of revolution. So let me go ahead and do the revolution. And notice there's another figure over here. I'll take it slow to do the revolution. So yeah, it kind of looks like a donut. Look, there's a hole in there. There's a hole. You know, let me kind of move this a little bit. You can see there's a hole. There's when you look at it edge on. So when you do the revolution, there is a hole. A hole is produced. This gives rise to the washer method. So I just wanted you to see a quick visual of that. Let's head off to the chalkboard now to generalize what we've just seen and come up with a new method, which is called the washer method. Now keep in mind, the washer method is nothing more than the disk method. It's just that the representative rectangle, it's perpendicular to the axis of revolution, but it's not touching the axis of revolution. So maybe there's going to be some subtraction involved here. But let's head off to the chalkboard to generalize this and officially write down the washer method. All right, folks, the washer method is really just an extension of the disk method. And we just looked at it in the interactive ebook. I said the washer method, it looks like when you do the revolution, you kind of get a donut. Remember, a donut has a hole in it. But that's why it's called the washer method. So to generalize what we just saw in the interactive ebook is if my rectangle is perpendicular to the axis of revolution, but it's not touching. It's not resting on the axis of revolution. When that rectangle gets revolved around the axis, it produces a washer or a donut. There's a hole in it. I've labeled from the top of the rectangle to the axis of revolution. I've labeled that with an uppercase R. That kind of reminds me that it's what I call the outer radius, the big radius. From the bottom of the rectangle to the axis of revolution, I'm labeling that with a lowercase r. That's the smaller radius, or it's the inner radius. So now let's generalize. Let's generalize the washer method. Here's the graph of, two functions. There's a region there. I don't know what the functions are. I don't care. I'm going to take this region and I'm going to revolve it around this horizontal line. So when I put in my one representative rectangle, and I label, that's the outer radius, big R of x. This is the little radius, little r of x, the inner radius. To get the volume, well, I would get the volume for the big R of x, pi times the integral a to b, big R of x, squared dx. So that's what the volume would be if there's no hole. But there is a hole. We subtract off the volume of the hole. The volume of the hole is pi times a to b, little r of x, squared dx. So I could write this as just simply one integral using a property of definite integrals. I could write this as pi, the integral a to b, big R of x, squared, minus little r of x, squared, dx. And this is the washer method. Key thing to notice about the washer method. The representative rectangle, it is perpendicular to the axis of revolution, but it is not touching the axis of revolution. That's what produces the hole. So let's head back to the slides and see what's next. All right, so you see with the washer method, what we've written on the board, the key is going to be the representative rectangle. If your representative rectangle is perpendicular to the axis of revolution, but it's not touching or resting on the axis of revolution, it's the washer method. And in using the washer method, you have to determine what I call big R and little r. Remember, big R is the outer radius. Little r is the inner radius. So let's look at an example. This will be an example using the washer method. Let's find the volume of the solid that's generated by revolving the region bounded by y equals x squared and y equals the square root of 8x. We're going to take that region, revolve it about the x-axis. So let's head off to the chalkboard to work through this example. All right, this example, we're asked to find the volume of the solid generated by revolving the region bounded by the graphs of y equals x squared, y equals square root x, and we're going to take that region and revolve it about the x-axis. Okay, so I've already graphed y equals x squared and y equals the square root of 8x, so it's this region right here that we're revolving around the x-axis. So when I put in a representative rectangle, I can put it in anywhere in this region that I want. When I put in a representative rectangle, the first thing I notice, that rectangle, it's perpendicular to the axis of revolution, but it's not touching the axis of revolution. Perpendicular to, but not touching, that tells me disk method. So for the disk method, I need to determine my big R of x and my little r of x. Remember the base of the rectangle is delta x. So here is big R of x. Big R of x. So basically it's from y equals square root of 8x to the x-axis. Well, that distance is square root of 8x. And then here's my little r of x. From right here to the x-axis. So my little r of x, well, it's from the curve y equals x squared to the x-axis. So that's just x squared. So, volume, I'm using the washer method. The volume using the washer method is pi, big R of x, squared minus little r of x, squared. And all I need are my limits of integration. So here, we can quickly determine the limits of integration. I can set the functions equal to each other. Here I would square both sides of the equation. I'd subtract the 8x from both sides. I'd factor out an x. Use the zero product property to set each factor equal to 0. I'd add 8 to both sides. And then take the cube root. So I know the x-coordinate of this point of intersection is 0. The x-coordinate of that point of intersection is 2. So that tells me the limits of integration are 0 to 2. And it's not too bad now. The square root of 8x squared, that's 8x. X squared squared. Remember, you multiply those exponents to get x to the 4th. Get an antiderivative. Antiderivative of 8x is 4x squared. Antiderivative of x to the 4th is 1/5 x to the 5th. And crank it through the fundamental theorem of calculus, and you end up getting 48 pi over 5. That's all there is to this one. So let's head back to the slides and see what is next. All right, that example wasn't too bad. Folks, I cannot stress enough how important it is to sketch the region and put in a representative rectangle. This is the key to all of these problems, and the next section as well. If the representative rectangle, if it's perpendicular to the axis of revolution, you're going to use the disk/washer method. If that rectangle is touching the axis of revolution, it's purely the disk method. If it's not touching the axis of revolution, perpendicular to, but not touching, then it's the washer method. So to drive this home, let's do one more example. So you need to write the example down. I'm going to ask you to do this example on your own. Then restart the video, and I'll be at the chalkboard working through it. So here's the example. Find the volume of the solid of revolution generated by revolving the region that's bounded by x equals 0, y equals square root x, and y equals 1. You're going to take that region and in part A, revolve it about the x-axis. Get the volume. In part B, revolve it about the line y equals 1. Get the volume. So pause the video, do parts A and B. Once you've done them, restart the video. I'll be at the chalkboard working through them to make sure that you got them correct. Okay, I asked you to work through this example where you're asked to find the volume of the solid generated by revolving the region bounded by x equals 0, y equals square root x, and y equals 1. You're taking that region and in part A revolving it about the x-axis, and then in part B revolving it about the line y equals 1. So I already have them graphed over here. So this is the region in question. I put in my rectangle, my representative rectangle. And I notice in part A, I'm revolving it about the x-axis. So in part A, when I revolve it around the x-axis, my representative rectangle, it is perpendicular to the axis of revolution, but it is not touching the axis of revolution. So that means in part A, I'm going to have to use the washer method. Perpendicular to, but not touching the axis of revolution is the washer method. So I need to determine big R of x and little r of x. So big R of x, well, that's from the top of my rectangle to the axis of revolution. That's not too bad. That's just 1. It's 1 unit from y equals 1 to the x-axis. Little r of x is, for this one, it's from the bottom of the rectangle to the axis of revolution. That's not too bad, because the distance from here to here is nothing more than square root of x. So for part A, using the washer method, the volume is pi times the integral, and my limits of integration, lower limit is 0. It's easy to determine what the x value here is. We know y is 1, square root of 1, 1. So x is also 1. So my limits of integration are 0 to 1. Big R of x squared, big R of x is 1, minus little r of x, which is square root of x squared. So we get pi times the integral 0 to 1 of 1 minus x dx. So that's pi, get an antiderivative. And when you substitute the 1 in and the 0 in, you end up just getting the volume to be pi over 2. Part B. Now in part B, let me get the blue colored chalk. Part B, we're taking the same region and we're revolving it around the line y equals 1. Okay, notice here that my rectangle, it's perpendicular to the axis of revolution, but it's touching the axis of revolution. So that means here, perpendicular to and touching, this is just the disk method. So I know the volume is pi, integral 0 to 1, r of x squared. But now, r of x, it's not this r of x that we did in part A, using the washer method. For part B, that's the radius of that one disk that would be produced when that one rectangle is revolved around the line y equals 1. So it's the height of the rectangle. Well, the height of the rectangle is just 1 minus square root x. It's the top curve minus the bottom curve. So it's 1 minus the square root of x squared. All right, we got to clean up that integrand. Let's see, pi, integral 0 to 1. We take 1 minus square root x and multiply it by 1 minus square root x. You get 1 minus 2 square root x plus x, dx. And, now when you, I would rewrite, let me put it in here. I would rewrite this as x to the 1/2. So now when I get an antiderivative, we have x. See the antiderivative here, so I'd add 1 to the exponent. That gives me x to the 3/2. A little multiplier out front would be the reciprocal of that new exponent, 3/2. The reciprocal of 3/2 is 2/3. So 2 times 2/3 is 4/3. And when I evaluate that from 0 to 1, I'll end up with volume being pi over 6. Okay, so this one example, it compared and contrasted the two different methods you know right now, the disk method, washer method, which are really the same method. Remember, the key is that representative rectangle. So one more time. If the representative rectangle is perpendicular to the axis of revolution, you're using the disk method or the washer method. If it's perpendicular to and touching the axis of revolution, it's the disk method. If it's perpendicular to but not touching the axis of revolution, it's the washer method. And in the washer method, you need to get the big radius, big R of x, and the little radius, little r of x. So hopefully you got parts A and B. But at this time, that's all there is in this section. So you should do all the assigned homework problems in this section so you can get your mastery for the disk method and washer method. So that's it for this section. Thanks for watching.